Hello, everybody, and welcome back to EM378SI Online. Make sure if you got questions, if you got problems you want to go over, or just want to see more content, get more review in, remember WebEx is happening Monday, Tuesdays, Thursdays of every week at these times in Iowa, or these Iowa times. So today, what we're going to get into is more of our friction coefficient, talking more about flow through pipes. So just as a general overview, if we're working with the Bernoulli equation, right, you have your P1 over gamma plus Z1, or just plus Z1 plus V squared over 2G. And then here you'll have some head loss. In this case, when we're talking about flow through pipes, our head loss is going to come from F times L over D V squared over 2G. Right? So this is just the length of your pipe, the diameter of your pipe, velocity inside your pipe. This F, though, is the only thing that's going to be a little bit tricky. Remember, if it's laminar, F is just 24 over your Reynolds number. But if we're talking about turbulent, things get a little bit different. For turbulent, you can either look at your function of your epsilon, which is your roughness, based on the type of pipe that you have or the diameter of the pipe, and then Reynolds number, and then take that to the Moody chart. Alternatively, if you don't want to do this, you can do what the Colebrook and Haaland equations. So for turbulent, another thing you can do, Colebrook equation. And these aren't things that you're going to be able to solve really algebraically. Let me just write them out here. So you'll just plug in what you know about epsilon over D, plug in your Reynolds number, and you'll get some F value out. Alternatively, you can use the Haaland equation, which is 1 over square root of F negative 1.8 log of epsilon over D over 3.7. This term to the 1.11 plus 6.9 over your Reynolds number. Now, these aren't exact. They'll give you an accuracy within plus or minus 5% or so. So you can use them for the purposes that we have. So yeah, you can solve for F. You can, you can have a good time that way. If your calculator can do it, this is a good job. But if not, then you can rely on this here or doing iterations on a Moody chart, which is what, if you've been watching lectures, which you should be, he went through Wednesday. So it's just all that stuff to keep in mind. But let's see this in an actual problem. This one's going to be a little more straightforward, just to illustrate the difference between friction, that head loss term, in turbulent versus laminar conditions. All right, so gasoline flows in a smooth pipe of 40 millimeter diameter at a rate of 0.001 meters cubed per second. If it were possible to prevent turbulence from occurring, what would be the ratio of head loss for the actual turbulent flow compared to if it were laminar? Alrighty, so what we're going to compare is head loss of turbulent over head loss of laminar. All right, so, and with what I just wrote on the other side, head loss is that coefficient times L over D, V squared over 2G. Here, since we're working in the same pipe, L over D, V squared over 2G. Turbulent is going to be the same as laminar. So really what this becomes is Friction factor of turbulent over friction factor of laminar. All right, so not such a bad deal. Let's start working on what this looks like, though. All right, so if we have laminar flow, that's just 64 over your Reynolds number. So for our Reynolds number, that's just rho VD over mu. And we can use, for gasoline density and viscosity, here are the approximations we're going to use, if I can find them. 680 and 3.1 times 10 to the negative fourth. Those are the numbers you're going to use. And then using that, I almost sneezed, but yeah, allergies. All right. Sorry about that. So 64 over, what is our Reynolds number once you plug in rho VD and mu. We also got to solve for V. So V is just going to be Q over A. And that is 0.001 pi over 4 times 0.04 squared. So the velocity that we get is 0.796 meters per second. All right. So plug all this number, and your diameter that you're given into this denominator, and you'll get 3.1 times 10 to the negative fourth. And you'll get that your friction coefficient for laminar is 9.16 times 10 to the negative fourth, I believe. Oh, sorry. This is supposed to be to the positive 4. There we go. So 3.14 times 10 to the fourth, not negative fourth. Sorry. So that's your FL for your turbulent. We're going to look at our Moody chart in this case. But here's the issue. What we're tempted to say is, since it's a smooth pipe, that means Ft is 0 because epsilon over d is 0. This is not true. Just because you have a quote-unquote smooth pipe, smooth does not mean epsilon over d equals 0. So just something to keep in mind, because in all practicality, there's not really going to be a pipe you're ever going to run into that has 0 friction effects on it. So even if you see something as a smooth pipe, in terms of using our Reynolds number and talking about our friction coefficients, epsilon over d is not 0, even if it's a quote-unquote smooth pipe. You know what I'm saying? All right. So you'll look up at the Moody chart, check your Reynolds number with your epsilon over d, and you should get f of t 0.0192. If you don't want to do that, you can always, if you don't want to use Moody chart, remember you can use Colebrook or Haaland equations, but those can be a little bit more of a pain in the butt to put into your calculator and kind of get a number that way. Alrighty. So our HL sub T or HL sub L is just the ratio of these values that we found. And so that's 21.0. So what we'll see is that the head loss of turbulent is going to be much greater than head loss if things were flowing in a more laminar way. which makes sense, right? If stuff is rumbling, tumbling through the pipe, you're going to get a lot of losses from bumping into the edge of the pipe. It's just going to be less efficient flow than if it were laminar. However, laminar flow is really hard to keep in a real world setting. So more often than not, we're going to see turbulent, but again, we know how to work with that, so it's not such a big deal. Alrighty, folks, that's what I got for today. Remember, Monday, Tuesday, Thursday, 6, 6, and 5 for our SI meetings on WebEx if you got questions. Next exam is on the 21st, so that's right around the corner. It's not next week, but it's the week after that. So I'll be setting up an exam review session and maybe putting out a couple more videos. I'll be putting out more videos for review next week, and then have a dedicated review time for this problem here. For the rest of the semester, we only have 2 chapters left. So that's pretty big. Because all we're going to do pretty much after this is lift and drag, and then also it's called open channel flow, and this is really helpful stuff. I saw a little bit of it at the internship that I did 2 years ago, and so yeah, it'll be a good time. But yeah, I hope to see you guys on WebEx. Keep watching these videos. If they're helpful, let me know. Or if you have any feedback in general, that'd be greatly appreciated. All right. Have a good day, everybody.